Hello everyone, welcome back to Introduction to Semiconductor Devices. So far in this course, we have studied some fundamental aspects of semiconductor devices. We understood how a PN junction works, and then we understood how a mass capacitor works. All of that lays foundation to understanding one of the most important semiconductor device, which is a MOSFET. It is not possible for us to really imagine a world without a MOSFET. A MOSFET has revolutionized semiconductors and it has paved way for the modern technological revolution. It is not an exaggeration to say that if there was no MOSFET, possibly there is no semiconductor devices right now. Okay? Or there is no, the information technology revolution would not have happened. It is that crucial. So today we'll begin our journey into understanding how a MOSFET works. So before we do that, let me start with a brief historical perspective. So back in the early 19th century, telephone was invented and then the telephone systems were being laid all across America and Europe mainly. Okay, and they were using vacuum tubes in the telephone systems to connect calls and to try to automate some of that. And those vacuum tubes were not very efficient, and people realized that there needs to be a solid state alternative to a vacuum tube. It was quite well known. And in the year 1926, a scientist by name Julius Lilienfeld, he had proposed the concept of FET, okay, which essentially stands for field effect transistor. Field effect transistor, and this was in 1926. And he proposed that you could use a combination of metal, aluminum oxide, and then cadmium sulfide. Cadmium sulfide is a semiconductor. So if you use this combination, you can demonstrate field effect, is what he said. But it turns out that this was 1926 and it was not possible to experimentally demonstrate it. He patented the idea, but experimentally it did not work. And almost 20 years went by without much progress. In the 1940s, AT&T Bell Labs was one of the foremost research organizations in the world. And Shockley was part of Bell Labs, and he had developed a lot of theoretical concepts necessary for understanding semiconductor devices. And he was also independently, I think, proposed the concept of an FET, and he was trying to demonstrate that. So the imperative to actually discover a solid state transistor was actually much more stronger by 1940s. So they were searching for this, and then there were many failed attempts. And Bardeen and Brattain also were contributing to this effort, and Bardeen I believe in 1945, proposed that there are these surface states in a semiconductor which are very important, and that helped them in the theoretical understanding. And finally, in 1947, Bardeen and Brattain invented what is known as a point contact transistor. I showed this image, I believe, in the introduction, but it was a replica. This is one more replica of the point contact transistor that was invented in Bell Labs. And if you look at this, it's a very crude device. Okay, so it had a piece of plastic, a triangular shaped wedge, which was coated with gold, and then at the tip of the this wedge, there was a cut. At the tip there was a cut here, and then essentially one side of it was like working like an emitter of carriers, and the other side was working as a collector. And this wedge of plastic coated with gold was pushed on a piece of germanium. This was germanium, and literally it was a base of the device. Okay, so it was pushed against this base consisting of germanium by a spring, and they managed to show transistor action in such a device. It was a very crude device. It was not at all reproducible, because if you shake it, the spring moves and then the transistor action is lost, and so on. It was not a very reliable thing. But this was the first device that showed transistor action. That is, if you control the current which was flowing into the base, you could, which is usually a very small amount of current, you could control a much larger collector or emitter current. That was the principle, and they could show amplification. Okay. So this was one of the most significant inventions in the history of transistor. This was in 1947 December, I believe, and in early 1948 1998 or so, Shockley, Bardeen, and Brittain came up with the concept of junction transistors, okay, bipolar junction transistors, which are known as BJTs now. Okay, and after about 10 years, they were actually searching, or they were actually trying to make a field effect transistor, but they could not make it work. Okay, and in the process, they happened to discover a bipolar junction transistor. And the challenge, as I said, was actually the interface between silicon and silicon dioxide. So whenever you have this interface between semiconductor and an insulator, that interface has to be extremely good. Okay, so back in Lilienfeld's concept, the interface between cadmium sulfide and aluminum oxide was not at all good. It was having a lot of defects and it did not work. And even whatever Bardeen Brittain tried also did not work. The breakthrough came when in 1957 or so, a scientist by name Atala, he was working on diffusion of dopants through a mask, silicon dioxide mask, and they noticed that if you have an interface between silicon and silicon dioxide, it had a very, very good quality interface. And that led, immediately to, the idea of a MOSFET, which is essentially metal oxide and semiconductor, right? So the MOSFET was demonstrated by Atala and Kang in 1959. So about 10 years after the invention of a point contact transistor. And immediately in a few years, Robert Noyce, who was actually one of the founding members of Intel, he proposed and demonstrated a concept known as an integrated circuit. So he integrated various MOSFETs on a single piece of silicon, and this was one of the first ICs that was demonstrated. It was demonstrated by Fairchild Semiconductor, where Robert Noyce was working at that point of time. Later, he split up. Him along with Gordon Moore and others, they founded Intel, okay, which makes all our processors even today. So you see, here is this idea of using a single point contact transistor having these elements is a very, very crude one, but quickly this idea of integrating these things on a single chip. So you see that there are multiple inputs, there are these transistors. You will understand slowly in the next couple of weeks why these what these things mean. Okay, we will talk about that later. But we had fabricated one of the first integrated circuits, and this was a very significant breakthrough in terms of science. And thereafter, it is essentially increasing the scale of these devices, or making them smaller and smaller. And by the way, the bipolar junction transistors were predominant in 1960s, but by 1970s, MOSFETs became the dominant technology world over. And today, you see that MOSFETs are the most commonly used device in semiconductors. Okay, so what are these transistors? Okay, when we can even think of junction FETs and things like that, but I'll just broadly talk about two classes, which are bipolar junction transistors, a BJT, and a MOSFET, okay, metal oxide semiconductor field effect transistor. Okay, so what is a bipolar junction transistor? Well, essentially it is consisting of two PN junctions. You could think of it like this, okay? So let's imagine that you have a N-type semiconductor. I'll make a P-type diffusion region in that. We talked about it when we talked about PN junction, right? Making a PN junction, you will diffuse a P-type. And after that, I'll again diffuse another N-type. So I'll have three areas, okay, corresponding to N, P, and N. That is one option. Or you could also have P, N, and P. Okay, these two combinations are possible. And schematically, you could show this as simply a piece of silicon consisting of three regions, N, P, and N. Or you could have P, N, and P. Okay, so three blocks. So essentially, you have two junctions, two PN junctions now, right? We understood how a single PN junction works, and a BJT is essentially simply two PN junctions. And you have again depletion and whatever we talked about, right? Forward bias, reverse bias, all that works in this also. Okay? And it turns out that one of them we call as emitter, one of them we call as base, and one of them we call as collector. Okay? So we can study this in greater detail, but in this course I have decided not to really focus on BJTs. The reason for that is, BJTs have been dominant in 1960s. After that, they are not that much used. MOSFETs are what are more commonly used now. And I felt that, I would spend time discussing MOSFETs in greater detail than actually talking about BJTs. I believe BJTs are part of the GATE syllabus in ECE or EE also, I believe, to some extent. But having understood the concepts of PN junctions, I'm sure you can follow up the concepts of BJTs by looking at some other material. I can also post some references for that, or even Pierre has it and Neiman has it. Everybody has some chapters on BJTs. You could read up a little bit about that. The basic ideas are that in BJT you could basically have three currents. Okay, I'm just giving you a glimpse of it. Later I will talk about it. So you have emitter current, and that will be equal to base current plus collector current. Okay, this is how it is. Emitter, base, collector, right? So usually the base current is a very small current, and by controlling the base current, we could control the emitter current. That's why you get the amplification. There's something called as beta and alpha. You can look up all that. Okay, it doesn't take you much time, but I would not cover that in this course. Okay. So what we will talk about in depth is a MOSFET, okay, which is basically a metal oxide semiconductor, which we already discussed the MOS system in, when discussing the MOS cap. And what we will do is a MOSFET consists of a MOS capacitor plus two additional regions. This we have already seen, metal oxide semiconductor. But now we are adding a N-type diffusion region and another N-type, two N-type diffusion regions. Okay, these are highly doped, high N plus it is, okay, diffusion region. Okay. We call them as source and the drain. One of them is called source, one of them is called the drain. There is no real, physically there is no difference between a source and the drain. It's just a matter of what voltage we are applying to it. Okay, that's why the convention comes about. But in terms of doping, typically they are symmetric. Okay, you can interchange the drain and the source and nothing much happens. Okay, the transistor would still work. All right, and then the gate anyway we have already seen, and we will also introduce another terminal now, which I mean in the MOS capacitor discussion we didn't mention it specifically. We just called it substrate. And now you could call it bulk or body or even substrate. Okay. So typically people don't use substrate because we tend to use source for S, for source. If you put substrate again, that becomes S and it's confusing. So we use bulk or body typically. Okay. So this we call as this is the D terminal, drain, source, gate, and bulk. And we apply various voltages to these four terminals, and that leads to some effects. So this configuration is called as an MOSFET. You know by now that NMOS is when you have a p-type substrate and you have an N inversion layer, right? That's why it's an N MOSFET. And you can have a complementary device which is a P MOSFET, which is consisting of N-type substrate and P plus drain and source. Okay, these diffusion regions are P plus. So that's it. So basically we have the MOS capacitor plus two additional terminals. Okay, so how does this help us? Well, to understand that, let's look at the structure in a couple of ways. Okay, we have already seen this side view, and if you take a cross section of a MOSFET, this is how it looks. We could also have a top view. If you look at it from the top, how does it look like? So it will be you have a gate which is having a certain length. So this is important terminology. So the length of the gate is essentially the distance between the source and the drain. Okay. So this is my length here. Length of the transistor. And this was only in 2 dimensions, but if you extend it into the volume of the semiconductor, into the paper, it's a 3-dimensional structure, and that 3-dimensional structure is showing you that you have this region again here. This is the width of the transistor. Okay. From the top view, it looked like this. So what you have is a wafer of silicon. You have source and the drain diffusion regions here, which are shown in yellow here. Right? These are highly doped diffusions. Okay. If it's a NMOS, it will be N plus. If it's a PMOS, it will be P plus. Okay. This is a diffusion region, and then they are separated. I mean, it's not really separated in the same plane. It's out of the metal is actually the gate is out of the plane. But when you look at it from the top, it looks like the gate is separating the source and the drain, but it's only from the top, right? Physically, we see that there is this oxide in between. Okay. So this is the top view, and you also have a 3D view, which is essentially showing you the same things. So you can have a length of the transistor, the width of the transistor, which is again another important parameter. Okay. So on a piece of semiconductor, I can make many of these devices. For example, if I take a wafer, I'll take one MOSFET, second MOSFET, and third MOSFET. I can make like many MOSFETs separated laterally, and we can connect them. And that is an integrated circuit that we talk about. So we are already doing it. Like if you take the most modern semiconductor chip, which is let's say an Intel processor, if you take a Xeon processor, it'll maybe be a size of 1 or 1.5 square inches, okay, and it'll have a few billion transistors. So many of these devices are integrated, and the challenge comes in how to integrate all of that. So, and we already told you that the essential physics happens within a few micrometers here. This is few micrometers. Okay. Below that, it's all just silicon, bulk silicon. Okay. So this is how a transistor structure looks. And these black things here you see, these are what we call as contacts. The reason is, if you look at semiconductor, we talked about some metal and semiconductor junctions, Schottky junctions, right? Or they can be rectifying contact or a ohmic contact, we say. So it is not enough to have a piece of semiconductor, but we have to connect it to the external world. Right? We have to connect it, let's say, to another transistor. How do we connect it? If we directly put a piece of metal, it will have a contact resistance. We mentioned this already. So now to avoid that, we can engineer these contacts in such a way that, I mean, one contact would suffice, but we just typically make more contacts to minimize the contact resistance. Okay. So, and these things I can connect. So this will be connected to a metal, another metal piece, and then so on. Okay. So that's how the transistors work. So this is a physical structure, but yeah, how does it operate? Okay. So this is again another view of it. Okay. So the same story that we've been talking about. So you have a substrate, you have a bulk, you have a drain, we have a source, and we have a gate, right? So essentially what you have is in between these two regions here, there is a junction. This is a PN junction, right? This is another PN junction, right? These two are PN junctions. In between them, you have a MOS capacitor. You could think of it like that, right? So if it's a ideal MOS capacitor, let's say, okay, there's no band bending at all. There are no carriers, nothing. It's an ideal MOS capacitor. Okay. The moment you apply gate voltage, what happens? If you apply a gate voltage, let's say positive voltage in this case, you can create, it's a p-type substrate. If you apply positive voltage, you'll create an inversion layer. Right? Let's say we apply gate voltage greater than threshold, then we have an inversion layer. So that essentially forms here below this. Just below the gate oxide, you will have an inversion layer. And what is the inversion layer consisting of? Well, this is electrons, inversion electrons. So what does it do when you have an inversion layer like this just under the oxide? Well, essentially you're connecting source and the drain. Correct? Source and drain, right? So current can flow from source to drain. But the moment let's say, make the voltage 0, this inversion layer disappears and there is no current between source and drain. This is the fundamental, in a very simple way, this is how switching happens. Okay. When, let's say, I assume ideal MOSFET. Okay. Assume ideal MOSFET. I mean, basically MOS cap, ideal MOS cap, and then there is FET structure. Okay. When you have such a scenario, if your VG is equal to 0, okay, I'll say Q inversion equal to 0. That means we could talk of drain current or source current. Both will be equal here because oxide is actually perfect oxide, right? There is no leakage. So typically source and the drain currents are equal. So I'll simply talk of drain current equal to 0. Okay. But when VG is greater than VT, Q inversion is not equal to 0. There is some substantial amount of inversion charge. So ID basically is not 0. So current flows. Okay. This is what we call as an enhancement type MOSFET. Why do we say enhancement? Well, there is no inversion charge at zero voltage, but the moment you apply positive voltage, we are actually creating an inversion charge. So in the at no voltage state, like Vg equal to zero, it does not conduct current, but the moment you apply a voltage, it conducts current. So this is called as enhancement mode MOSFET. But if you remember, you don't need to have this as a scenario all the time, because we already studied the CV, right? We said if you have a Vg like this, and let's say this is C, okay? If you take an ideal MOS capacitor, let's say the CV is something like this. I'm showing the LFCV. And this was your VT. And let's say this is your Vg equal to 0, okay? Or 0 volts, so yeah. So now at Vg equal to 0, the device is maybe mildly depleted, but it doesn't conduct current. There's no inversion charge to conduct current, right? This is how a CV could look like. But we also saw that there can be many things like metal work function difference, and then there can be also some fixed oxide charges, because of which you may not have this condition, but you might have a situation where your CV looks like this. Okay, you get the drift. I mean, this is depletion, this is inversion. Okay, I'm sorry, it looks very bad. Let me. Okay. So this is basically with some work function differences. Okay, let's say it's non-ideal, and this was ideal scenario. So if you have some sort of a shift in the VT now, right? Because VT now has become close to 0. So even if you don't apply any voltage, there would be an inversion layer. Okay. So here you have, okay, N channel without Vg, or at Vg equal to 0. You have a connection. So you don't have to apply any voltage, it will simply conduct. But then if you apply negative voltage to this, then you will push the, sorry, if you apply negative voltage, you will push the electrons away, and then you will have the channel removed. Okay. So in this case, let's say if Vg equal to 0, there is Q inversion is not equal to 0. So ID is not equal to 0. It is conducting when there's no voltage. But then a Vg is less than, let's say, negative. Okay, I'll just say that much. Okay, it has to be sufficiently negative. Then Q inversion is equal to 0, because it pushes away the electrons, and then this depletes the substrate. Okay, ID equal to 0. So we have to deplete the, you have to push away the inversion charge and deplete it. So this is called as a depletion mode MOSFET. I would say this is mostly academic. It's not really, we will typically deal with enhancement mode. We don't really worry too much about depletion mode. Okay. So yeah, this is how the basic structure of a MOSFET looks. Okay. So in the next video, I will talk about the various current conduction mechanisms or current conduction modes in a MOSFET. All right. So I'll see you in the next video. Thank you.